In this video, we will talk about generation of random numbers and elements of probability. In probability theory, the sample space of an experiment or a random trial is the set of all possible outcomes or results of that experiment. We're going to use set notation here, and it's common to refer to a sample space by omega. Some examples of discrete sets are a coin toss where you have head or tails, and we can denote that as 0 or 1. So the sample space is omega, and that's the set of the numbers 0 and 1. If we have a dice with 6 faces, the sample space is this set of numbers 1 to 6. You can also have continuous sets. For example, all the real numbers from 0 to 1, or all the real numbers from minus infinity to infinity. We're going to use capital letters. That's a typical way to denote random variables in some probability theory texts. We associated a probability, that's the odds or relative frequency, with possible events. And a probability density function, or the density of a continuous random variable, is a function that describes the relative likelihood for this random variable to take on a given value. So, for example, for continuous sets, the probability of a single point is 0. So that's an infinitesimally small probability of having a specific value x, small x. Now, the probability of finding a value between x and x plus delta x, that's finite, and that's given by f of x times delta x, where f of x is called the probability density function, or the PDF. If we sum over all these small intervals and use the definition of a Riemann summation for an integral, then it follows that the probability of finding a value between, let's say, a and b is given by the integral from a to b of f of x dx, where f is the PDF. And the PDF is always normalized to 1, so the integral from minus infinity to infinity of f is unity by definition, because the total probability has to be 1 or 100%. For discrete sets, we define the probability distribution as P of capital X equals little x, where x belongs to this set omega. And let us supply a few definitions before we give a few examples. So the expectation value is the sum over all of x times P of x in the discrete case. And in the continuous case, that sum is replaced by an integral. So that's an integral over x of f of x dx. So that's the expectation value, or the average value of x. The variance of a distribution is defined as expectation value of x squared minus the expectation value of x and all squared, where e of x is defined using these two formulas we used before. So that means e of x squared is given by sum in the discrete case, or an integral in the continuous case, and we're basically weighing x squared with a probability for each x. And here in the continuous case, the infinitesimal probability is f of x dx. So we're weighing it by this infinitesimal probability as indicated here. Okay, so let's consider some examples. So let's consider a Bernoulli distribution. In Mathematica, you can simply type Bernoulli distribution, but you will not get anything back. But if you type PDF, let's suppose we ask for the probability density function for the Bernoulli distribution with variable p, then we get the definition of that distribution as a function x. That's a function of x. We can explicitly declare that this is a function of x, like this, or we could do it like this, declare that it's a function of x. In either case, we get the same thing. So let's try this version. So this is the definition of a Bernoulli distribution. It's a discrete distribution. So x can take the values of 0 and 1. That's like the coin toss here. And the probability of x being 0 is 1 minus p, and the probability of x being 1 is p. And of course, the total probability is the sum of those two possibilities, so it's 1. We can toss a coin 20 times. So let's do this here. So let's toss a coin 20 times. A way to do this is to use the command random variate in Mathematica and then say Bernoulli distribution. The probability p is 50% here for each face of the coin, each side of the coin. So that's 1/2. And then we can specify how many times you want the experiment to happen. And we use Shift Enter. And here we have 20 coin tosses. And you can run that again and you get different random results. We are going to discuss further how to sample distributions in the next video. For now, let's talk about the distributions. You can also ask for the probability of certain outcomes for a certain distributions. For example, you can ask for the probability of x being 0 when x is distributed. You can use the symbol distributed according to a Bernoulli distribution with probability p. So if you execute that, Mathematica will tell us that the probability is 1 minus p. And you can ask for the same thing and ask what is the probability of x being 1. Mathematica will tell you that it is p. So Mathematica can calculate probabilities for you from distributions, but we can also do this calculation explicitly, and we will show how. We can also ask for the mean of the Bernoulli distribution, for example, and the mean is p. So for coin, the mean is 1/2. That's the mean between head and tails. And we can also ask for the variance. So that we can simply say variance, and Mathematica will calculate the variance for us. If you want to find out more information about this probability command and how to get this symbol, you can use probability question mark and then click on the documentation, and then a window will pop up and you can look at the details here. And this x distributed according to some distribution can be addressed like this, or you can copy paste it from the documentation. Okay, so let's close this. And another quantity you can calculate is the CDF, or cumulative distribution function. That's the integral of the PDF. So let's ask for this. And Mathematica will give us the CDF for this distribution. We will go into more detail in a little bit when we discuss the CDF for continuous distributions. Okay, so now let's discuss continuous distributions. The first that comes to mind is a uniform distribution. So again, if I type uniform distribution in Mathematica, the default is a uniform distribution between 0 and 1. And if we want to get the PDF for that, or the probability density function, we can type PDF. And we can specify that we want the variable to be x, to be specific. And Mathematica will tell us that the probability density function is 1 if x is between 0 and 1, and 0 otherwise. We can define this to be a function. Just for convenience. And then we can check, for example, that the integral between 0 and 1 of p of x dx is equal to 1. So the total probability is normalized to 1. We can also plot p of x from 0 to, let's say, 1.1. Okay, and that's the probability. We can use the filling to make this more obvious. So that's p of x, and it's 1 between 0 and 1, and then it's 0 everywhere else. We can also ask for the CDF, or the cumulative distribution function. So let's call it C and replace P by C here. And Mathematica will integrate over the PDF from -infinity to x, and will give us this result. We can also get this result by explicitly integrating the PDF. So if this is analytically possible, which it is in this case, we can do the integral from -infinity to x of p of x, or let's change variable and call it y, dy. But of course, here Mathematica is having some trouble. It doesn't know how to handle this integral from -infinity. So it's complaining about knowing whether x is real. We can try using assumptions. So let's use assumptions and then say x greater than 0 and y greater than 0. Let's try this. And this helped. So let me suppress this. And so we got this result. But actually this had the side effect of eliminating the other cases. So we have either x is greater than 1 or true. So let's just not make these assumptions, but instead let's assume simply that x belongs to the real numbers. Let's try this. And that was a weaker assumption. So now we get these 3 cases, and you can check that this result is the same as this result. So the CDF, or the cumulative distribution function, has this form, which is basically integrating over this from minus infinity to x. Okay, so let's try another PDF. Instead of taking the default that's from 0 to 1, let's suppose that we go from 2 to 7. Then the probability is 1/5 when x is between 2 and 7, and 0 otherwise. So in that case, we shouldn't integrate from 0 to 1. We should integrate from 2 to 7 basically. But even if we exceed that, you can integrate from 0 to 10. That's not going to change the result because the probability is 0 outside 2 and 7. So that integral is still 1. And let's try and plot this result. Now we see the probability is 0.2 between 2 and 7, and 0 otherwise. And of course the 0.2 happens so is such that the total probability is 1. So Mathematica has normalized the distribution so that the total probability is always 1. And we can again ask for the CDF if we want to. Now we have to change the uniform distribution to be between 2 and 7. And of course we can do this again. And we should get the same result as when calculating the CDF explicitly. Okay, so now let's consider a more realistic example of another distribution. So let's consider the normal distribution, or the Gauss distribution. You can call that using PDF of the normal distribution in Mathematica, and you can specify the mean and the variance like this. So these are the two parameters you have to specify. And then we can, as usual, specify that we want it as a function of x. And here I'm going to plot 3 different versions. So I'm going to plot the Gaussian distribution for 3 different values of sigma. So let me do this. So that's for sigma 0.75, and the other one is for 1, the orange one, and the green one is for a sigma equals 2, which is more spread out. And I'm also plotting the CDF, or the cumulative distribution function. And you can see as I'm integrating for small x, the value is 0. And as I keep integrating, I approach 1 asymptotically. And if the normalization of this distribution is 1, then if I integrate from minus infinity to infinity, I should get 1. So for all CDFs, we expect them to go to 0 on the left limit when x goes to minus infinity, and we expect them to go to 1 on the right limit when x goes to infinity. We can also define these to be functions. So for convenience, let's call the normal distribution for a mean mi and a variance sigma, and let it be a function of x. And we can also define the CDF, or the cumulative distribution function, for the Gauss distribution. So here we get explicitly the formula for the Gauss distribution that we know from textbooks. And here we get the CDF. Now, a lot of textbooks say that you cannot get the CDF explicitly or analytically for the Gauss distribution. This is not quite true. You can get it. The integral is called the error function, and there are tables for this function. But of course you have to use tables to evaluate this function. So these functions are defined in Mathematica and MATLAB and Python and so on. But if you use some older language, you may have to use a library that will have this function in order to use it. we can explicitly calculate this. So let's try and do it. The integral of f of x from minus infinity to x. That's the definition of the CDF, the cumulative distribution function. So let's try and do this integral. Mathematica is calculating. And this is the result. So it had to consider several cases. It doesn't know that sigma is a real number, so it took some time to calculate this result. So we can simplify and speed up this calculation if we explicitly tell Mathematica that sigma is a real number and that is positive. So I can just say that it's positive and then it knows it's a real number. So I can either use the command assuming and then sigma greater than 0 and then the command in here. If I do that, it will only make this assumption locally for this command. So if I do that, Mathematica will do the calculation a bit faster and will give me this result. You can actually check that this result and this are the same. We will check it in a minute. Before we do that, let me just say that I can use this command $assumptions equals, and then inside curly brackets I can put my assumptions or a list of assumptions. I can also say that me belongs to the real numbers, for example. So I can do that, and then it has my assumptions here, and then these will be used globally everywhere. So then I can try and do this integral, and these assumptions will be used automatically. And just remember this error function, we can use the help. So the error function is defined here, and RFC is a complementary error function, and you can look at the documentation and the details and see that RFC is 1 minus RF. So the complementary error function is 1 minus the error function. So we know here if we replace RFC by 1 minus error function, we will get this result. So we can try and simplify this result. It didn't simplify, but okay, let's try and subtract c of x. And we get 0, so we know the difference is 0. Okay. So now let's suppose that I want to calculate the probability that x is between the value me plus sigma and me minus sigma. You can always do that by calculating this integral. So if we look at our shape here, let's say in this case when sigma is 2, and that's for the green curve, and the mean is 0, so me is here. So we are calculating the integral from here, from -2 up to 2, basically, of the green curve. That result should be around 67%. But let's calculate it and see what it is. So we can ask Mathematica to explicitly calculate this integral analytically from me minus sigma to me plus sigma. So let's try this. It will use these assumptions that we've made before, which makes the calculation easier. If we hadn't done that, it would give many cases just like before. So now it was able to calculate this integral analytically. And I can say %/n, And okay, we see that this is around 68%. Now for any distribution, you can also say use the probability command to calculate this quantity. So I can say what is the probability of x being between me plus sigma and me minus sigma when x is distributed according to the normal distribution with mean me and variance sigma. So I can ask for that, and Mathematica will immediately calculate this integral for me. Again, it does this simply by doing this integral. Actually, you can also do that using the CDF. So essentially, that's what Mathematica does. So it knows what the CDF is and uses that to calculate this integral. So essentially, if I take the CDF at me plus sigma and subtract the CDF at me minus sigma, we know the CDF is the integral of f of x. So this definite integral is simply the difference of the CDF between this point and this point. So if we do that, let's try that, we get this result, and the minus can come outside. We can simplify this result, and then we get the same result as before. Okay, so that concludes this video. In the next video, we will describe how to draw samples from distributions and how to do histograms.